Ladies and gentlemen, before the event begins, a quick safety notice. We are not expecting a fire drill this evening. Should the alarm sound, emergency exits can be found either side and to the rear of the auditorium. In the event of a fire, leave the building by the nearest exit and follow staff instruction. Thank you for your attention and please enjoy the event. Please welcome your host, Marcus Iannone.
Hello everybody and welcome to the Lancashire Aerospace Society event 2026. Aerospace is increasingly in the public eye as humanity prepares to return to the moon in NASA's Artemis program, but ignoring that for now, ever so slightly closer to the Earth, aerospace is helping to prepare the next generation of industry professionals. Over the past year, the Society has participated in a range of projects that have allowed its members to gain very practical, valuable experience. From the National Rocketry Championship, flying mid-powered rockets over 50 competing universities, our IMEC UAS Challenge team has also designed an unmanned aerial vehicle to a brief provided by the Institution of Mechanical Engineers, and of course the Mach 26 team, who have designed high-powered rockets to launch at the Machrinash spaceport in Scotland to a target apogee of 3,000 metres. We will also hear tonight from our special guests in our panel section. You can submit your questions with the QR code that will turn behind me in a moment, but to open our event this evening, please give a very warm welcome to the Associate Dean of Engineering and Computing, Dr. Sravanti Sashkumar.
Hello. Those videos that were just shown to us, fantastic work, students, very well done. Once again, a very good evening, distinguished guests, industry partners, colleagues, and most importantly, our students. Welcome to the Lancashire Aerospace Society's annual networking event. Tonight is about celebration, celebrating achievement, commitment, and potential. Our aerospace students are amazing. I'm so proud of you. You are those budding engineers who are already demonstrating industry readiness. Well done, everyone. Hands on heart, I'll admit, studying engineering and aerospace isn't easy. It's academically, it isn't easy. It requires discipline, problem solving, teamwork, and resilience, especially when solutions are complex and uncertainty is part of the process. The students receiving awards tonight have gone beyond what is required. You have demonstrated not only academic excellence, but curiosity, leadership, and the ability to work through challenge. These awards don't just recognize what you've achieved so far, they reflect your potential to shape the future of this sector. The future needs you. Today I was asked to share a personal reflection, and it's about, does engineering need women? What is their role in engineering? So, a question to ask: does engineering have a gender or gender bias? Earlier in my student life, I found myself as the only woman in an engineering class of 76 students. No one explicitly questioned my presence, but belonging is not only about what is said. Sometimes it's about what you don't see and how you feel. What made a difference for me was seeing another woman who was confidently leading technical discussions and being listened to as an expert. That visibility has changed my sense of what was possible. It wasn't about preference or privilege. It was about realizing that engineering was not just a space I was allowed to occupy, but it's what I enjoyed the most and felt passionate about. And it is genuinely where I felt belonged. And this is why women in engineering matter. We need women because engineering needs the full range of human talent and perspective. Aerospace problems are complex, high stakes, and systems driven. These problems demand diverse ways of thinking, questioning, and designing. When women are missing from engineering teams, we risk losing perspective that affect innovation, safety, sustainability, and ethical decision making. I hope you all agree with me on that. Diverse teams don't just look better on paper, they perform better, solve problems more effectively, and design solutions that serve society more fully. So here's a message to women students here today. Your achievements are evidence that you belong here, evidence that aerospace is stronger because of your contribution to everything that's happening here and in the wider sector. There may be moments of your journey where you may feel doubting yourself or your place in this field. When that happens, remember this evening. Remember that your success opens doors, not just for you, but those who will follow you. To all students who are here today, the future culture of aerospace will be shaped by you. Be the colleagues who value difference, challenge assumptions, and create inclusive teams. Excellence in engineering is not just technical, it's collaborative, ethical, and human. Congratulations to each and every one of you for what you have achieved so far. We are proud of you and excited to see the future that you will help build. Enjoy your evening. Thank you.
Thank you so much, Associate Dean, for being ever so brave and presenting first. And now we have the very first of our team's presentations for the evening. Allow me to introduce Ari Smith and Alex Gilmore of the NRC team, who will deliver the first of many tastes of rocketry tonight.
Hello, good evening everyone. I'm Alex.
And I'm Ariana.
And we are the Vice Team Leads for the University of Lancashire's National Rocketry Championship team. There we go.
Here is Team Belka, the team leads and associates. And here is Team Strelka, the team's leads and associates.
So, what is the National Rocketry Championship? Well, it was founded in 2013 and it was held from October to June on Wednesdays every Wednesday. It's teams of up to 10 people per team, and it is hosted by the UK Students for the Exploration and Development of Space. For this year, our target apogee is 2,200 feet or 670 meters, and it is UKSED's most popular competition with over 50 universities and 250 participants.
To begin, let's expand a little on our objectives. A few of our objectives are to successfully launch a mid-powered rocket to around the height of 670 meters, carrying the customer payload and avionics, while gathering flight data to be displayed after the flight. A few things to think about is temperature, humidity, pressure, air quality, and height using Morse code.
So let's move on to the history of the team in the competition. So last year it was the Rocketeers in 2025. So overall it was a successful year for the project. There was a successful test launch and a successful final launch. But really what that year acted as was some lessons learned for this year, especially with the strong manufacturing and design methods that were displayed, such as the use of OpenRocket, SolidWorks, the use of 3D printing as well. And of course, the second years this year, who were first years last year, have passed on some really useful information. We're both first years, and the second years, I can say, have really helped out with this year.
This year, the team has doubled in size to over 20 people, being split into two teams. Two teams meaning two rockets. While following a strict budget and the risk assessment, now to explain how our teams have worked. They've been split into 4 sections. This is design, manufacturing, avionics, and simulations.
So to start off with design, so we used software such as OpenRocket and SolidWorks to make the rocket. And really the approach we use is an iterative design. So what we have happening is the design team is talking to manufacturing and testing. They relay information between each other about feedback from testing, what needs to be changed and what is fine. And then we can redesign as required. UKSED sets the strict requirements for values such as stability and length to diameter ratio. And like I said, the iterative process is made easier through the use of 3D printing. So it's a rapid manufacturing sort of system, so we can 3D print the nose cone, the customer payload, and the avionics. And this is an enlarged version of the design here. So I'll go over sort of the top. So we've got the nose cone at the very top, and then in green is our customer payload, which is supplied by UKSEDS. Then just below that, where that tube inside the rocket is, that's the avionics bay. So that provides power to the customer payload. That is a requirement set by UKSEDS. That also has the sensors for the temperature, air quality, etc. And then below the avionics is where the parachute is, so that will deploy at apogee. And then below that is the motor assembly, where we use the G79-10, which is a rocket motor that has a 10-second delay.
Now we have the manufacturing team. They will be working with programs such as ArcSlicer to be able to 3D print different parts of the rocket in different materials such as PETG and PLA. They also use the laser cutter to be able to cut parts such as the fins in carbon fibre or the thrust rings. When we are at the point of putting the rocket together, they help guide the other parts of the team that aren't usually involved in this section into where they need to go and what they need to do. That can include decorating the rocket with spray paint or electrical tape, or that could be sanding it down to make sure it fits into the other parts.
So this is just a few images of the manufacturing process. So you can see those 3D printed parts there can print within hours. So that's just kind of a really good demonstration of the iterative process that we can have. And then the other image on the right is the motor assembly with thrust rings running all the way through.
Next we have avionics. Avionics create the most essential part of the rocket as they work on the PCB, which is the printed circuit board with sensors and powers. The avionics bay provides power for the customer payload, and avionics also includes the GPS, which aids in locating the rocket after it's launched. And all data that is recorded is collected and analysed after recovery.
So this is just an example graph, an altitude plot from last year's rocket. So you can see it matches what a regular flight of a rocket would be. That massive jump in the fluctuation of the altimeter there on the graph is just a pressure jump. When the rocket separates, the pressure changes rapidly, and that's explaining the massive jump there. And then the next one, which is the pressure plot, similar before, it's basically an upside down version of the altitude plot. You can see the slight fluctuation at the bottom for the exact same reason. It's just the massive pressure change when the rocket separates and the parachute deploys.
Now we have simulations. Simulations work from when we first finalise the design to when we finish working on multiple parts, which helps the designers and manufacturing progress as they do the simulations to understand and make sure that everything is plausible. They do this by using a program called ANSYS. The simulations they create allow them to see different outcomes by using CFD to find different velocities, magnitudes, and systems.
And then finally, the launch itself. So we've just had the test launch last Sunday, 10th of May 2026. And then we have the final launch, which is set for the 17th of June 2026. I also want to touch on some of the trips that we've managed to do this year. So the society as a whole, including NRC, attended the National Student Space Conference hosted by UK SEDS in London. So over 15 NRC members attended the event. We're planning to do something similar for next year, and we also would like to explore the possibility of more trips in the future. And that's it. Thank you for listening.
Some very interesting work there from the NRC team. Thank you, Ari and Alex. We now move on to a guest presentation. The spirit of ambition in the society is epitomised by the university's motto, ex solo ad solem, from the earth to the sun. We now journey to the sun, so please join me in welcoming the expert on the sun, the star, not the newspaper I hope, Associate Pro Vice Chancellor Professor Robert Walsh.
Hey, can you hear me now? That's great. How are you doing tonight? Thank you very much for asking me to come this evening and to tell you a wee bit about what I do. And I don't know why it's doing that. It doesn't like it for some reason. But I really want to tell you a wee bit about the science that I'm involved with and the things I am now engaging with here at the university. And it's great to hear so much about the rocketry there. I've been down at one of those SEDS conferences. It was in Manchester, the one I went to and was speaking at, and I know the enthusiasm and just the whole energy in that particular environment of our students really understanding what it means to engage with space. I'm in charge of our new facility called Altitude. Some of you in this room have probably been out to it and actually been able to have a chance to see what we do out there. We say that we're shaping tomorrow's skies with our indoor flight arena, what we've got in regard of the classrooms and new teaching spaces and laboratories that we have there, particularly one around a beyond visual line of sight work with uncrewed systems. There's also a bit of space stuff. We're building a CubeSat teaching laboratory there as well to really get an idea of what it means to get your hands dirty with stuff that's actually really going to go into space. But I was asked this evening to tell you a wee bit about what I do and how I got to where I am, I suppose, as a professor of what is really solar astrophysics. And I'm a mathematician by background, can you believe it? And then I went more towards the sort of physics side, and now with what I'm doing, I'm sort of intersecting physics and engineering, and it really shows that, to be honest, as scientists, we have an opportunity to engage with lots of different people from lots of different backgrounds. And you'll find that hopefully in your careers, that there's not just one discipline will solve the big challenges that we have in our world today. It is a multidisciplinary approach. But let's, for the next 10 minutes, 15 minutes maybe at most, let's look at what it means to try and spend some time at the sun. I do this sort of thing. There we go. Oh, no volume up on that. But you've already seen some. Oh, jeepers. There we go. I'll wake you up. Two, here we go. Ever so slightly bigger than the rockets that we have with our student groups, but this is a sounding rocket program which I work on with NASA Marshall, and they use this for training their astronauts, for training the scientists to be involved in what it means to engage in these sort of big engineering programs, and if nothing else, try to get an idea of what it means to actually fly something into space, even if it is just a suborbital. My expertise is this. This is images of the sun. This is really what your sun looks like from space in extreme ultraviolet light. This is from the NASA's Solar Dynamics Observatory, a mission that we've been heavily involved with here at the university. And all we see about the sun now, with the incredible data we've got, means that when we use rockets, and from the collaborations that I have, we're actually taking some instrumentation, trying to test it using the sounding rocket program, and then trying to see what we can understand about our closest star. There we go. Go on. There we go. Here's an image from the Hubble Space Telescope, which I know in some respects has probably been superseded by James Webb, but still from an optical point of view, this is an amazing instrument which has really transformed our understanding of the universe. This image here is known as the Hubble Deep Field, and this is around about the size of a patch of sky, about the size of your thumbnail. So if you held your thumbnail up and you held it over that bit of the night sky, this is sort of the size and scale that you've got here. And virtually every single dot that you see here, this bright dot, is a galaxy. And there's thousands and thousands of galaxies here. Some of the brighter ones maybe are stars. You can see them closer to us. But every single dot there is a galaxy with hundreds of millions of stars actually in it. If you speak to my colleagues in the Jeremiah Horrocks Institute in the School of Engineering and Computing, then you'll get a feeling, that, well, how do we understand all of those sort of stars and objects? How can we get a handle on what they're like? And one way to do this is to use something called a Hertzsprung-Russell diagram or an HR diagram. Really what you've got here is on the vertical axis, you've got the brightness of the object you're observing, and on the horizontal axis, actually going in the other way, so temperature goes from right to left and increase. You have the temperature of the star, and you can use spectroscopy to be able to pick that out. All very exciting. You've got big blue stars, the high temperature ones up in there in the top left. You've got the red giants there over, and then the top right. But sort of in the middle of it all, you have this sort of bog standard, ordinary, very, very, not very exciting, but close to us star. And that's our sun. And thank goodness it's a bit of bog standard. It's not too big, it's not too small, doesn't rotate too quickly, doesn't throw out too much energy. Well, say a bit more about that in a minute. It really is a common or garden star. But of course, it's in our own astronomical back garden, and therefore we can use satellites, we can use ground-based observations. I tend to spend most of my time in space with the sun, but also sounding rockets to try and understand and unpick what it means for our sun to exist. Now, when I do these sort of talks and trying to give you a bit of a context of what's going on as we actually head into the instrumentation itself, maybe we can look at by thinking about what the context of that is, even just within our own solar system, with the 8 planets that travel around the merry dance around our star. So here they are. Here's all the planets at the right sizes on the same sheet of paper. You know, you got Jupiter, the big one there with a big red spot. You got Saturn with its lovely rings. Wonder if you knew that Uranus and Neptune were so large compared to there in the 5th place, which I used to say was just outside the Champions League places, but now you can get a Champions League place for doing anything really, can't you? So in the 5th place, we have the Earth. If you put the sun into this particular picture, then it looks like this. 99% of the mass of our solar system exists within the star. You can actually fit 109 Earths across the diameter of the sun, 1.3 million Earths in the volume of the star. And this is the object that provides the light and heat and energy that we require for life on Earth. So it's important we understand it, but it's also important we realize that even compared to our own planet, the energy, the necessity of what it means to be connected to this star is so very important. We've got a whole fleet. Oh, why is it doing this? This is very strange. We've got a whole fleet of instrumentation which are observing the sun at the moment. And we're part of that. Actually, here at the university, we have several different collaborations with missions with the European Space Agency and with NASA and the Japanese Space Agency, JAXA, in order to actually understand the star. And in particular, what on earth is happening here is really about, dear me, let me go down here. Sorry about this, folks. Not too sure what's happening here, folks. Let me just see. Can I go out from that? There we go. Let's see if I can. Transitions, is it? Where would it go? Set up a slideshow, isn't it? And then don't use timings. There we go. Hopefully that will work. There you go. Let's try that now. So we have all this fleet of instruments that really are really pointing out what the sun looks like for us and helping us to understand that. And in particular, we really are trying to understand how the sun affects us here on Earth. That's some of the work that we've been doing in order to try and really pin that down. You know, we sit in the habitable zone around our star. That's the sort of the region of space, the sort of three-dimensional ring, if you want to call it like that, there around the halo around the sun, where liquid water can exist on the planet. And of course, we're now looking for planets around other stars, exoworlds or exoplanets, and the habitable zones of those stars are where we think that you will find potentially a planet that could have life. Who knows? That's what they're looking for at this moment in time. We've only one example, and that's ourselves. One way to look at the sun is to look at the photosphere. This is the part of the visible light from the sun that your eyes and my eyes are attuned to. Never look directly at the sun, damage your eyes. But if you've got a telescope and special filters on it, this is sort of what you would actually see. And the sun actually does rotate in front of us. It takes about a month to make a full rotation. So we're not actually seeing the same face of the sun all the time. It's continually changing. And of course, that has an effect upon us here on Earth. And superimposed upon that, you have these dark dots. And they change and they evolve over time, particularly quickly, actually, and they're called sunspots. Here's an actual sunspot. Gives you an idea about what a sunspot actually looks like. You have this sort of dark region at the center. It's a big magnetic patch, essentially, a big magnetic pipe poking out of the surface of the sun. And then at the outside of it, the magnetic field goes up and arches down, and that gives you that sort of ballerina skirt fluted pattern around it. To give you an idea of size and scale, you could easily bowl the Earth into that dark region. And the thing is, the number of sunspots doesn't stay the same, it changes. So in this graph here, this diagram, in the vertical axis is number of sunspots. In the horizontal axis, it's years. So that's from 1700, not 5 o'clock, but 1700 a year. Right up to 1880, then 1880 round to the present day. And you see this natural up and down from solar minimum, where there's hardly any sunspots, to solar maximum, where there's loads of them. And when you have lots of sunspots, that's when the sun is really magnetically angry. That's when it's throwing out lots of big solar flares, solar storms, and of course that affects us here on Earth. In fact, if you fly in a bit closer, that's where we are right now, really. There's 2014 up to 2026. This is from the 1st of January, actually, so it's a wee bit out. But it gives you an idea we've passed through the last solar maximum and we're heading down towards another solar minimum. Though that doesn't mean that the sun is not as angry as it could be, and it's not going to do things it shouldn't do. In fact, as the sun relaxes away from this sort of high energy state, that means there could still be some large eruptions heading down towards the Earth. And of course, when that happens is when the fun really starts. We call these things solar storms. These are huge instabilities of magnetic field that throw out thousands of tons, tens of thousands of tons of electrified gas, plasma, out into space. And it is something which is really quite dramatic if you can catch one of these actually going off. And one way to actually look at it is actually to create an artificial eclipse. This is again on another satellite mission where you block out the bright disk of the sun and you look at what's happening around it. Another engineering feat, really, because you're trying to stabilize, firstly, the mission. Then you've got to actually make sure you've got your telescope in the right place so you can block out the bright disk, and then you use a detector which has a gradient on it, actually, of detection from the bright bit at the center right the way out towards the edges, which allows you to see something like this. The continual streaming you see is the solar wind flowing out from the star. We can now measure that, see that, and understand that. But also these huge big eruptions, these bubbles of gas that come out, and these are what we term solar storms. And they're the things that affect us here on Earth, and the whole range of electronics and engineering and other aspects we have there. Of course, remember, you can fit over 100 Earths in that disk at the center. These are eruptions that are thousands of times bigger than our own planet. And the fun, as I said, begins when one of these heads down towards the Earth, an Earth-directed solar storm. This is not to scale. It takes light about 8 minutes to travel from the sun to the Earth. So these big eruptions often take 1 or 2, maybe 3 days. And how effective they are and how they can affect satellites or anything like that is really due to how much mass they're carrying, basic physics, how much the speed they're traveling at, and actually the direction of the magnetic field relative to the Earth's magnetic field. Because we're fortunate. We have our own sort of Star Trek force field around our planet, which does protect us from these solar storms. But sometimes if they're just the right energy, and they're just the right size, they're just carrying enough mass, and the magnetic field is just in the right or wrong direction, depending on how you look at it, the Earth's magnetic field rings like a bell, slams into it, and the energy particles can actually travel down the Earth's magnetic field and hit the Earth's atmosphere. And that's when things happen down closer to the surface of the Earth. One example being the aurora borealis, or the northern lights, all due to the fact that the particles in the Earth's atmosphere get excited by these energy hits from the sun. They gather that energy, then they release it in wave packets of light in green and pink and red, depending upon the constitution of the atmosphere at that point. Beautiful byproduct. If you ever get a chance to see the northern lights, grab it. It's an amazing experience. I'm sure some in the room tonight have actually had that chance. The trouble it is, and this is where it becomes more engineers are more worried about this, as well as general solar scientists, is you wouldn't want to be in this, on a spacewalk from the International Space Station, say, when one of these is actually hitting. The amount of radiation that an astronaut would experience can quadruple in a matter of tens of minutes. And there's actually a shielded part of the station where the astronauts can hunker down into. It's a bit like a fishing boat out at sea in a storm. There's nothing much you can do. You got to batten down the hatches and see how things develop. course, it also affects satellites, particularly the fragile, instrumentation that could be in it. The electronics get fried, the solar panels and get move and actually have a bit of a problem in regard of actually orientating themselves. And that's quite dangerous, just because we actually rely upon satellites more than ever now. And as you see, that's something which the UK in particular is very concerned about, is we rely upon satellite communication for a whole range of different purposes. And in fact, the Artemis mission, you mentioned it before, but the Artemis mission, because they go around the moon, actually go outside the Earth's magnetic field for a short period of time. And they were lucky that this time there wasn't a large solar flare going off, but if there was, the way that they had to deal with it in their small compartment was simply to actually try and pack the walls around them with bits they had with them. Would you believe? Not very technical. In order to actually see if they could shield as much as possible from a solar storm. Thank goodness they didn't need to do it. Here's the path of the moon's orbit, for example, through around the Earth. And there's times when the moon's orbit is within the Earth's magnetic field and times it is outside of it. And in fact, we're trying to put a lunar base on there now. There's engineering challenges as to what are you going to do when you're there? How are you going to deal with the radiation changes that long, the temperature, and the fact that you've no atmosphere, you've no oxygen, you've got to manufacture it. What about the water? How do you do all the things that you would need for a lunar base? These are all really, really challenging things to consider, but they're the engineering problems we're dealing with now. Severe space weather is important. We have a whole range of different ways in which space weather can affect us and affect a whole range of industries, both in regard to energy industries. Last thing you want is your power lines to have conducting high electric currents because of a solar storm. It has happened, particularly in northern latitudes like Canada. But also your satellites go down, your GPS goes a bit funny. You increases the amount of radiation you experience as a passenger on an aircraft, particularly if it's flying over the polar regions. So aircraft now reduce and go to lower latitudes and change their flight plans. There was a large solar storm happening, etc., etc. And in fact, the UK has decided, he says, hopefully, if it will change. Oh, there we go. On its risk register, which the UK has something called the National Risk Register. Most countries do. But you can actually go online, you can type this in, see what you can get, and it tries to measure the impact of a particular risk that the country has versus the likelihood it's going to take place. Now, these numbers are very small. You should have brought your telescope tonight to read this graph. But if you just look at the boxes, I suppose, and I picked out a couple of here, then the green one is an earthquake, okay? It's down there in the bottom left-hand corner. The likelihood of it happening, very low, probably very localized. The impact of it is probably going to be not very much. On the other hand, if you look at pandemic, which is way at the top, then it has a huge impact. It'll create a large thing over a large area. We know that in regard to what's happening in recent times. Or terrorist attack, that's the red one. It may have a huge impact, but it could be really local. The other one after is a severe space weather storm, which is there just in the blue side of things. And it's just beneath the pandemic. Oh dear. And that's basically because we are quite vulnerable. If it was a large event which was Earth-directed, then it could actually have a severe effect upon the technologies which we use every day. And therefore there is a real sense that severe space weather and trying to predict it and trying to actually work so we can actually minimize and be more resilient towards it is very, very important. And in fact, that's what we do in our sounding rockets. One of the sounding rocket programs, the very last one we've done, is actually we've taken a couple of rockets and we're launching them so we can try and understand the initiation of some of these particular solar flares. And this program here at the University of Lancashire really started back in 2012, which is a long time ago. Here's the first team. We all had a good time. There's a lot of people. You've got to work with a lot of people to launch one of these things and understand what's going on. But it worked really well, and we launched our rocket, and it was brilliant. Really, really good. And we got a lot of papers out from it. We thought this is brilliant, and the team were really part of what's going on. So we decided to do it again, because we got this sort of NASA Group Achievement Award, which, you know, it showed us that we had the capability to do it, and actually it was something very worthwhile pursuing. So we did it again. This is actually in 2016, just about 10 years ago. We have done several since then, but these are the ones I wanted to show you. Here's the team. We got the team back together again. There on the far left was Darren Ansel. You may know Darren as a professor of aerospace, as we looked like 10 years ago. Then at the other end, you've got Ben Watkinson. That's what he looked like 10 years ago. So you can come and have a good look at that if you want. I'll just embarrass Ben in front of you. And we all got that, and it was brilliant. We thought it was working very well, and it didn't work. The rocket launched okay, but the actual instrument shutter didn't open, because as you can maybe see here at the bottom there, one of the clamshell, sort of backshell type things was tightened too much. It shorted the electric current essentially connected to the shutter, and the shutter didn't open. Okay, and that's tough to take. You know, we took 3.5 years to really put this together, and at the end of it all we've done is tighten the thing at the back too much. It happens, because rocket science isn't easy. It's difficult, and the guys and girls have been really involved in it. You know, the students have been really involved in the rocketry program here. You understand that there's sometimes things just don't work, and you realize and you learn from that one after another. And you know, success is built on a series of failures, and if you don't fail, then you don't really learn anything. And you know, from this we learned a lot in regard to what this mission was about and why we were doing it and how we can actually be better for what's going on. And we did. A couple of years later, we launched it again, and from that we had a better instrument, we had a better launch, and we had some better results. In fact, these here are the highest resolution images ever taken of the sun. There's only about 5 minutes worth of it, but it's 5 minutes of really good data that has actually made a difference to our understanding of the star. So, if you have these sort of things, and you know, things do not always go right. Life is not linear. It's a long, linear, messy process. Research and being involved in these sort of projects, whether you're in industry or whether you're in academia, you know, do take twists and turns. It's how you learn from that and how you build upon those successes. So that's a wee bit of what I do. And I've been excited to be not just involved in a bit of modeling and simulation, which is what I used to do when I was doing the mathematics, right through to the physics and the instruments, and now looking at the engineering of what it means to actually launch a rocket. I hope you've maybe grasped a wee bit more about your star this evening. But more than anything else, as the introducer of this session said, you know, the university's motto is about stretching from the earth to the sun. And in some respects, that's not just, you know, a saying for, well, you know, that's a very nice thing to do, a Victorian way of thinking about things, which is where, of course, the university came out from. But rather, I think it epitomizes what we try to do here at the University of Lancashire. We want you to reach your full potential, for you to be able, as far as you can, to stretch out from the earth and to the sun. And I hope with all that's been happening as you finish off this year of your studies, whether you're going on into your second year or third year, or maybe you're going to be graduating very soon, we very much want you to be that success. So that's all from me. Have a wonderful rest of the evening, and thank you for giving me this opportunity to tell you about what I do with rocket science and how we observe our closest star. Thank you.
Many thanks to Robert Walsh for that very informative presentation. I'm going to pretend I knew a single thing of what was on about this then. But back to Earth's lower atmosphere, we now enter the world of drones with our IMEC-E UAS team. This year, they've designed their own aeroplane, and I'm going to pretend I know anything about that. But people who actually do know about that, here to tell us more are Safa Shireen Peruntail and Matthew Jerem.
evening. My name is Shuri and I'm the team lead for our university's 2026 IMechE UAS Challenge. Alongside Matthew, today we will be introducing the competition, this year's mission requirement, our team structure and the development of our 2026 aircraft platform. So, what is IMechE UAS Challenge? The IMechE UAS Challenge is an international engineering competition where teams design, manufacture and operate autonomous unmanned aerial system over a year-long project. This year, 55 universities are participating, including more than 15 international teams. The competition involves realistic mission tasks such as autonomous navigation, search operation and payload delivery. What makes the challenge particularly valuable is that it follows a structured engineering process similar to industry project, requiring teams to complete multiple technical deliverables throughout the year. The challenge then ends in a final fly-off judged by aerospace industry experts, where teams are assessed not only on flight performance, but also on safety, technical competence, and overall engineering approach. So this year's mission focuses on an agricultural operation where the aircraft must complete both autonomous and manual flight tasks, navigate through predefined waypoints, and dispense a water payload accurately. The system must also support multiple payload releases during a single flight. Alongside the mission objectives, the aircraft must also satisfy several operational performance constraints. These include maintaining a maximum takeoff mass of 10 kilograms, while also achieving a minimum flight endurance of 15 minutes with 20% battery remaining. The aircraft must also operate with restricted speed and altitude limit, while also being able to take off and land within a confined area. The competition also introduced several technical constraints that strongly influence the aircraft design, such as the payload must be inserted from the top and the entire system must fit within a specified transport box dimension. The aircraft is also required to support toolless assembly and disassembly, making modularity and accessibility an extremely important factor. Additionally, the use of off-the-shelf composite structures are restricted, which significantly influence our manufacturing process this year. Taking all these factors into consideration, our design philosophy focused on developing an aircraft that is simple, efficient, and easy to integrate. Our teams is divided into several groups, each responsible for different aspects of the aircraft development process. As the team lead, my role involves project coordination, team management, and overseeing the overall competition progress. The design team focuses on the CAD development, structural analysis, and aerodynamic calculation. Whereas the payload team is responsible for the agricultural mission system, including the tank and spray mechanism, payload deployment, and the electronic integration. The manufacturing team handles aircraft fabrication, assembly, testing, and structural integration. Finally, the avionic team develop both autonomous and manual flight system, communication system, and the integration between the payload electronics and the aircraft avionics.
So, as you can see, this is last year's design. It had a completely different set of design requirements, so they were aiming at delivering a payload through a parachute by dropping it from the bottom of the fuselage. So it features a high wing, a U-tail, and it's a tail dragger. So there are a couple issues with that design that we found after flying it. So one of the main things was our structural components for the wings were made out of 3D printed PLA, which ultimately deemed the failure of the aircraft as it broken. But there are a couple of other key metrics which we learned from that, one of them being our tail boom design was causing a flutter while flying, which was causing a lot of instabilities, and our fuselage itself wasn't large enough for good integration of the payload and avionics. So moving on to this year's aircraft design, we focused on optimizing the tail boom to basically rectify the issues we said earlier about fluttering while flying, so giving much more stable flight. And our fuselage is much more simple, allowing for a better avionics integration, so we've got a dedicated bay for that now, and our new water system has enough space. Our overall structure is now strengthened so we can support this extra mass from the water. So one of the key components to designing this aircraft this year was making it modular. So some of the key aspects of our modularity are we need a completely detachable wing and tail section so it can fit in the transport box, and we need a hatch that goes into the top so we can actually insert our water payload. So last year's design featured a completely foam wing, a monocoque structure for the fuselage which was made out of fiberglass, and 3D printed joints for the structural components. So this year we're focused on strengthening it up and going for a much more simple design. So we're going for a much more traditional wing design, making it out of ribs and solar film in it. These ribs are made from ply, and the same goes for the fuselage being made from ply and also being covered in solar film. So all of our structural components are now made out of aluminium to support the load and make sure nothing breaks. And like I said before, it's a much more modular design. So for the actual competition this year, we're focused on flying safely, consistently, and stably. So that's in both testing and our competition flights. We're hoping to hit all of the targets during the flight and enhance our integration of the avionics within the system. Thank you very much.
Thank you to the UAS for showcasing your excellent work this year. Thank you both to Shireen and Matthew. Both teams that we've heard from so far have explored some very different corners of the aerospace sector, showing real breadth from the industry. But still to come, we have a presentation from our MAC team, who last year achieved the closest to their target apogee of all the entrants, followed by our awards segment, where outstanding contributions towards this year's projects will be celebrated and recognised. And finally, our expo section at the back, where we will have the opportunity to see the impressive work that the Society does in person and chat to some of our members. But first, it's time for our panel section, where I'll put your questions to our special guests. And without further ado, please give a very warm welcome to our special guests, Ian Martin, David Gonzalez, Dave Terry, and Mark Potter. Yeah, anywhere you like. Hello, how are we all doing today?
Good, thank you.
Good, gorgeous. So our first question for tonight is, how do you think that AI will impact the industry, if at all? That is for any of you to answer. You can all answer if you'd like.
I think Mark Potter, ex-BAE, now retired. AI is going to affect everything. There's no doubt about it. It's going to absolutely revolutionise everything. Even when I was at BAE 5 years ago, we were starting to play with AI to read engineering drawings that were 50 years old and convert them into 3D models. The technology was in its infancy then. Going forward, I can see that AI will be designing aeroplanes. You'll give it a set of design rules, and it will follow those rules just like designers do, and it will generate all airframes, systems. It will revolutionise everything, but it will still need the engineers to manage that process and be the reasoning behind what the AI produces. As we all know, AI can produce rubbish. So I think one of the big advances will be actually making AI programs that police AI programs. So basically you give an AI program carte blanche, but you have another AI program that's actually policing it with rules to make sure that it stays within the rules.
It's like a good cop, bad cop situation type thing. Oh.
Sorry, not saying I wonder what's going on. Probably everyone can hear me anyway. I'm quite loud-mouthed, to be honest. I think AI, typically, it's quite a broad title. It's quite a broad area and understanding and kind of appreciating what we're talking about in AI is quite challenging itself. But I think it's important to understand and use AI as a tool, an aid. It will support, it'll make things quicker, it'll make things more agile, it'll give opportunities for people to develop and explore things like any other tool does. So I don't think it's necessarily something to be frightened of. I don't think it's necessarily something to be caught up in all the headlines that you hear. I think many of you are probably using AI to a greater or lesser extent in most of your everyday life, and I don't think that's going to change massively with industry. I think, you know, there's a lot to come and a lot to see, and a lot of what we don't know will come ahead of us. But yeah, I think that's what I'd add to that.
It's interesting. I joined an AI board for the Engineering Council, and the Engineering Council has made the decision that AI is a force for good. So they are actually encouraging AI and everybody to use AI. But there is worry that obviously there will be people that abuse AI. So I think at the moment there's going to be a lot more rules around using AI to stop it going AWOL. But it's quite interesting, when I was in the AI panel, lots of the UK AI experts were in that panel. And the first thing we had to do as a group was actually define what AI was. And all these leading AI specialists said, you cannot define AI. It moves too quick. Every time they try to define it, the following day it's different. So it's still moving, it's still progressing, we still don't know where it's going to end up. But it is to be seen as a force for good.
Yeah, once regulated and stuff as well, isn't it?
Sorry?
Once it's regulated and stuff as well,
Yeah.
it'd be easier to put into whatever engineers.
I mean,
do.
regulation is coming on even now.
Yeah.
People are starting to regulate.
It'll speed up things. It'll give us the chance to try things which we've previously dismissed, things which would have taken too much evaluation previously. It'll now open opportunities and also hopefully take out some of the graft which is really unnecessary, but in the past has been necessary. Things like, you know, doing some of the detailed drawings and things like that, where it's been vital in the past, but a machine can do that. It doesn't need an engineer to think of ideas. So it's opening up opportunities for engineers, as well as hopefully taking away from some of the more menial tasks. But the overall effect will be to increase the speed and rate of improvement, and that's what engineers do. We improve the world. So that's and solve problems. So it'll give us more tools to do that.
Yeah, I would have to agree. It's more likely that it will improve productivity for engineers. It will allow engineers to summarize analysis that could be days, weeks, months of data focused into succinct data sets. And as with most things, it will evolve. Everything evolves all the time, and you will find that what you learnt yesterday will be out of date the day after. And it's a matter of making sure you're up to speed, aware of the pitfalls as well as also the benefits, and also using it responsibly.
Yeah, we can agree on that, can't we? So, next question. What role do professional institutions play in an engineer's career progression today? Anyone's welcome to answer that as usual.
That one. So I was heavily involved at BAE at a time when BAE didn't see the value of professional registration. That changed massively overnight with the Haddon Cave inquiry, where an airplane crashed and people were killed, and there was a massive inquiry called Haddon Cave. And out of that inquiry came a lot of recommendations, but one of them was that engineers should be professionally registered. So there was a massive drive within the aerospace industry to become professionally registered. There's still a massive drive, and in fact now, if you have got signature approval on an engineering project, it's mandatory now that you have to be professionally registered.
So, from the point of view of the IET, we hold regular sessions on professional registrations and progressing your personal career through its lifetime. We hold workshops for people to get their careers written down in a formal method so that they can eventually, hopefully, achieve chartered engineership and then expand their careers and also their education as well.
We can help on several levels, the institutions. They can help during your education in providing access to libraries, things like that. We can help by allowing networking for visits, events, people. We have contacts all over the place, so that, you know, if someone comes to me and says, I want to talk about an expert on medical devices, it's not my field, but chances are I'll know somebody who knows somebody who is an expert on that field. When you come to applying for a job, the things like the challenge, which is sponsored by the engineering institutions, it's valuable experience that employers are looking to find. So it's good for your CV, it's good for that interview. Now when you've got your job and looking ahead, like my colleague says, I'm a chartered engineer. What does that mean? I've done a degree which proves my ability to learn, but I've been assessed by other competent engineers, and they have checked that I can actually do my job. So it's a proof of the ability to do your job. So it can, I think it can help on several levels. And the more you ask from the institutions, the more you get from them. If you join the local teams, you can find out, you can get into places, you can organise things with a professional institution backing you. You get a lot of more recognition and acceptance for things like visits or information. There's also well, a couple of more areas. By the networking, you can solve problems, get solutions. You can find people who will help you in your career. And so somebody asked me, they had a particular problem to solve. Did I know anybody who would help them? Yes, I did. I gave them, it was an adhesives problem. So it helped them solve a problem which made them look good in their career. And the other thing, I was one of your colleagues from a couple of years ago applied for a job, a very good job, a really good job. And I was able to offer him a reference from my position as regional chair of a professional institution. And I hope and believe that may have helped him get that job. So we can help on a lot of levels. So it is very relevant, I believe. Thank you.
Anything you want to add? No. So, next question. What challenges does the industry face today where the opportunities actually are? Like, where do we actually get those opportunities? Like, the job market seems so saturated these days with not many jobs coming through. How can engineers go around that?
There's a question and a half, isn't it? And I think probably it would pay to, it helps to define that a little bit more. But looking at the context of yourselves coming through as future engineers, I think it pays to be flexible, to be adaptable, to be open-minded in where and what you want to be doing and where you want to be going. Now, we live in an area. Lancashire is predominantly focused with large organisations. We've got some key organisations like obviously BAE in the region. We've got Leyland Trucks and other large organisations in this area. They're not the only place. I won't be thanked by people from BAE for saying that, but they're not the only place. And it's about being flexible, about being open and thinking about what you want to achieve within your own careers and what you want to get out of it. And I think, you know, for some people, organisations, large organisations such as BAE are fantastic places that will give you a really defined, clear career path. But for other people, that's not going to suit. And you're going to find opportunities in some of the small, you know, really innovative, really driven, really exciting SME, small manufacturing and engineering organisations around here. You know, being flexible to what it is you're looking to do, you know, where you want to specialise, that is where you're going to find the opportunities. That's where you're going to be able to really carve out your own career path, I would say, if that's what the question's looking for.
One of the things that, as a graduate at this university about 25 years ago, my first thing I would say to anyone that's graduating is basically broaden your horizons. Don't focus on one small area. Be willing to move around, be willing to learn, and be willing to accept that you don't know everything. And also one other thing is, sometimes it's good to be a small fish in a big pond, as well as being a big fish in a small pond, but just literally be aware and be flexible as much as possible.
That's good advice, I would say.
Yeah, I can probably add a little bit to that as well, in that being in a big organisation, I grew up in a big organisation, progression is slow, and you do wonder whether it would have been better to have joined a smaller company and been able to shine a bit quicker. There's a lot of people to surpass when you're in a big industry, so don't be put off. All industries are fantastic.
I'd like to agree with my colleagues that you need to be flexible and don't be put off by the requirements necessarily on the jobs which are out there. A lot of employers write the job spec for their ideal candidate. They seldom find their ideal candidate. And often you may be that candidate they're looking for, because what they're looking to find is somebody who can do the job. And with a good degree behind you, which you'll get here, you've got the ability to learn how to do that job. So don't be put off necessarily by detailed information on that application form. And as I say, be flexible. Maybe try an industry that you wouldn't normally consider. Give it a go. You'll get experience, you'll get understanding, you'll get learning, you get something to put on your CV, and then you give yourself time to find maybe the ideal job. And believe you me, when you leave university here, you don't know where exactly you want to be. Your objectives will change as you get older and you get more experience. You'll find, I did a degree in agricultural engineering. I've never worked in agricultural engineering. I've no regrets. I worked in automotive engineering. I didn't know when I left university that I wanted to work in automotive engineering. So give yourself the opportunity and don't dismiss things just because it doesn't fit your ideal image at this time, because it might change.
So for our next question, our last question unfortunately, if you could ban one phrase from LinkedIn, what would it be? I think I know mine.
Open to work.
Yes. Because who's not?
Do you know what? It's clear. I've not got one phrase, and I'm not going to restrict it to LinkedIn. It's cliches. I'm a dynamic, hard-working team player. Honestly, everyone puts that. It really doesn't matter. It really doesn't impress. It really doesn't appeal. Just be yourself. Be honest. LinkedIn, LinkedIn is one path, but you know, what makes you stand out on LinkedIn is probably not single phrases. It's actually where you contribute, it's where you comment, it's where you actually add value. And it's the same with applications. It's the same with everything, really. Avoid the cliches that everybody uses, because all it does is turn people off.
Your value is in what you've delivered, not in what you think you are. It is actually in the things you've delivered and how good you are at delivering that makes the difference.
I would agree with that, yeah.
I'd say one other point, and that is also your connections benefit you as well, and peer feedback on you, how you work, how you've delivered things is also more important than, as I said, the buzzwords. Buzzwords are generated, can be generated from AI, but people's feedback can't be.
Yeah, I don't like a buzzword, mate, because they're never accurate, are they? You just say one thing on your CV and then you get something else from they're in the enduring room and they're sat like that. You don't want to be there.
Can I add one final piece of advice from me? We talked earlier on about how AI is going to affect engineering and things like that. A lot of you will be using AI. Please, for the love of God, don't use AI for your presentations and your applications and things like that. As an example, I recently interviewed and recruited some interns. I had 9 applicants for a role where we were set a task. 8 of the presentations were almost identical. People that didn't know each other, came from different places. The actual slides were the exact same ones because AI had generated them. Out of the 9 people, guess who got the job? It was the one whose application was different.
It was made by a person. Right, we do still have a minute left. Right. Well, if you guys are ready, then we can end this here if you would like. Or do you have anything else that you want to add?
Anything they want to shout out?
Anything you want to shout out? Anything at all?
Who's your favourite engineer?
There we go.
Brunel.
Brunel.
Babbage.
I haven't got one.
Too many to choose from.
No, I think Brunel for me because just his vision. In actual fact, his biggest projects didn't work, and he nearly died digging his tunnel. But yeah, just the guts of going for the impossible almost.
Yeah. Right, unfortunately we will have to end that there. Thank you for your time. Thank you for the questions, everybody, as well. Let's hear it for our lovely panel for today. So that was our lovely panel for tonight. Did we all enjoy that? Did we all get some lovely information from him? Yes, gorgeous, lovely. One more applause for our guests. Brilliant, brilliant. So now we'll move on to our MAC team, who work with the largest and most powerful rockets that the Society handles. This year they've designed a 2-stage launch vehicle to hit an altitude of almost 10,000 feet. Please welcome to the stage Eleanor Foley and Lily Gabrielides.
Hi, my name is Eleanor and I'm the team lead for the MAC project.
And I'm Lily and I'm the CANSAT team lead.
So what is MAC? MAC is the UK's high-powered rocketry competition hosted by Exotopic in Scotland. There are over 30 entries each year with some international teams competing. At the event they host a variety of space skill workshops and have guest speakers present to give information about what it's like to work in the aerospace industry. Some key information about the competition. All the rockets aim to launch between 2,000 and 3,000 metres, and they must carry a CANSAT payload of over 1 kilogram. There are 2 categories in which you can compete in, Category 2 and Category 3. Last year we competed in Category 2, but this year we are competing in Category 3, which is the innovation category with the 2-stage rocket.
So this slide is showing how we've progressed as a team from our first entry in MAC 24, as shown by the first image, where you can see a relatively small team and rocket. And then we improved on this for MAC 25, where both the team size and rocket size increased significantly. And we've taken it even further this year by creating a 2-stage rocket, which fits into the 3rd category. So this is a video showing the AI terrain detection software on last year's launch footage. or should be. So we've got quite a few aims this year. The first of which, as previously mentioned, is to compete in Category 3, which is an improvement on our previous 2 entries. We're hoping to launch the first successful 2-stage rocket at the MAC competition. We're aiming for an apogee of around 2,500 meters to 3,000 meters, and we're hoping to also improve our outreach and engagement.
So this is how our team is structured. So as I previously said, I'm team lead for the project. My project manager is Tyler Moses, who is in the audience today, and he will be team lead for the MAC 27 project. Then the team is split into design and manufacture, propulsion, CANSAT, avionics, and CFD. The design and manufacture team are primarily responsible for the CAD model, which is later used for manufacture. The propulsion team are responsible for the motor selection and design of the motor retainer. The CANSAT team are responsible for the payload, which carries the sensing systems to collect atmospheric data. The avionics team are responsible for tracking, deployment, and recovery of the rocket, as well as AI integration and imaging. And the CFD team are responsible for airflow simulations and drift calculations. There's also some names of some of our academic mentors up there. This project wouldn't have been possible without them, so a massive thank you to them as well. So this shows how our design has progressed from when we first entered the competition in MAC 24 to now. As you can see, our design was significantly smaller in MAC 24, but obviously bigger and better each year. So this year's design is based on the design from MAC 25, which we had a massive success with. So we have taken this design and added a booster stage to the bottom to go into the innovation category. The lower stage houses an L1000 motor, and the upper stage houses a J415 motor.
So here you can see the design progression of this year's rocket, with the initial design being on the top and the most recent one being on the bottom. The main difference is the sustainer body tube diameter is now the same as the booster, and the fin orientation and shape has also changed as well.
This is a CAD model of our design this year. So as I previously said, there's an L1000 on the lower stage and the J415 on the upper stage. There is a set of fins on each stage. The CANSAT can be seen at the front of the model, and the avionics bay can be seen in the middle.
So this year's rocket will be separating into 3 different stages. The booster will be separated using drag separation, which should occur around about 1,500 meters. The CANSAT and drogue will then be deployed at apogee. The CANSAT parachute will be held and then deployed at 500 meters. Similarly, the main chute will be deployed at 400 meters, both of which will be using a Jolly Logic.
We have already had so many successes throughout our project so far this year, from securing external funding from companies such as RS, Mercer, and a private sponsor from within the team, as well as getting approval on our design from the RSOs. We've also managed to improve our outreach and engagement, which is fantastic for inspiring the next generation of Rocketeers. But hopefully our biggest success is yet to come. We have recently began our manufacturing stage, and our competition is in less than 2 months. So wish us the best of luck, and thank you for listening.
Some very impressive work from our MAC team there. Thank you, Eleanor and Lily. And now we move to recognise the extraordinary contributions of our individual team members. Many of these projects would not be able to make it to launch without the extra work and effort of these people, so it's only right that we celebrate it. And here I'll welcome the NRS team to start the rewards.
So, I'm honoured to introduce the awards tonight for NRC. So the first thing we need to do is introduce the VIPs who will be giving out the awards to the winners today. So that will be Darren Ansell,
Sravanthi Sashakumar,
and David Gonzalez. If you could please come up, please. So while we're doing that, so I'd like to introduce the Above and Beyond Award, which is presented by Darren Ansell. So this is for someone who has committed a lot of their own free time to the competition, someone who has, after all of the problems and things that or the challenges that we've faced, someone who has gone and done a bit more extra work to alleviate the pressure on the whole team. And the winner is Matt V. Laitkin. Yeah.
Next, Next, I will be presenting the Outstanding Contribution Award, which will be presented by Sravanthi Sashakumar. This is for a person who spends hours outside of society time to work on this project, is always asking questions about this project, and has gone as far as to use their own 3D printer to print out parts when they had failed originally. This is for Isabel Pye.
And the final award for NRC tonight is the Excellence Award. So that is for someone who has delivered the highest quality work, and I've witnessed it, the whole team's witnessed it. Someone from manufacturing who always can follow the task to the T and deliver the highest quality, whether if that's 3D printing, water jet, cutting the fins or anything like that. And the winner of this award is Matei Garcia. And now it's time for the UAS Awards.
So for our awards, we'd like to invite up on stage Charlie Griffiths, Ian Martin and Dave Terry. So the first award for UAS we're giving tonight is the Excellence Award. This person has gone above and beyond, really being the backbone of the team, especially with the avionics design. This will be given by Charlie Griffiths, and it's to Rachel Loftus.
Next, we would like to recognize one of the team members for his outstanding contribution to the project. This award goes to Sean Dunn for his dedication, hard work, and commitment throughout the development of the aircraft. His contribution played a major role in the project so far. And I would like to call Ian to give this award.
So the last and final award for the UAS is the Adaptive Excellence Award. This will be given by Dave Terry. This person has gone above and beyond, really stepping out of their comfort zone, learning entirely new disciplines of engineering, specifically moving from robotics to more mechanical-based design. And this is Jeffrey Bird. So that concludes the UAS Awards. We'd like to welcome Mac on stage to give theirs.
I will now be presenting the awards for the MAC team. So could I please welcome the VIPs to the stage?
Robert Walsh,
Nigel Whittaker,
and Mark Potter.
Our first award for tonight is the Commitment Award. This member of the team has gone above and beyond at every opportunity, ensuring we meet all of our deadlines and giving support at every hurdle.
This award goes to Jake Baker.
Our second award for tonight is the Resilience Award. This is going to a member of the team who has worked tirelessly on the CAD throughout the year as it has been improved and updated without complaint.
This award is going to Cameron Hume.
Our third and final award for tonight is the Adaptive Excellence Award. This award is going to a member of the team who joined us later in the project, but has learnt quickly, adapted to new situations, and contributed effectively to the team.
This award is going to Benjamin Nadekani.
That is all from us. Thank you so much for listening, and we will now hand you back to the host.
Now we have reached our final presentation of the evening. of course, not our least. Please put your hands together for the CEO of Northwest Aerospace Alliance, Paula Gill.
Thank you. Good evening, everybody. Have you all enjoyed yourselves so far? Come on, come on. Have you all enjoyed yourselves so far? Good. Okay. I'm a little bit disappointed. I'm a bit disappointed because we've just had some amazing awards for some amazing people. We need to do that again. But we can't do that again. We haven't got time and we'll be in trouble. But what I'm going to say to you is this. Tonight we've had some fantastic award winners, some fantastic students, and they're part of some fantastic teams that have done amazing work. What I want you to do, please, with me now, is to cheer for all of those people that have won awards and their teams. Let's have it. Well done, everybody. Whoa. That is more like it. We should have been hearing that the whole time. So, for all of you guys out there that have won awards and the teams that have participated in the competitions and worked with the award winners, I just want to say from the bottom of my heart and the people in this room, you are amazing and you are our future. And we've heard that throughout this evening through the speeches that we've had. But none of it would be possible, actually, if you didn't have the support of the lecturers and the professors and the mentors and the industry partners. So I also would like you to do the same thing and let's thank them. Let's say thank you guys, all of you. Let's cheer for them too. Good. That's good. Now that's what's called collaboration. We work together. Students, professors, mentors, industry leaders coming together to make our future great, but doing it together, making sure that you know what we need and we know what you bring. Because actually, what you bring creates what we need. You change our future, you change what we need. Engineering is a profession, like a doctor or a lawyer or an accountant. But we don't always think of it like that. And we've got to change the way we think. You know, you are the future. And everything that happens from here on in is because of you. And it's because of these people down here that support you. So if you take one thing away from tonight, other than the fact that you are absolutely brilliant, all of you, it's that always remember the people, the professors, that sat with you whilst you talked about yourselves and whilst you talked about your wants and your needs for your future and what you think you can do and what you can bring. And remember that those people have been sat where you sat at that point, and they've gone out there and they've experienced the world differently and they've had different experiences that they're sharing with you. Professor Robert Walsh. Professor Robert Walsh amazes me. I mean, I'm not a scientist, I'm not an engineer. I tried to be an engineer, but they kicked me out, but that's another story for another day. Professor Robert Walsh teaches me something every time I sit and speak to him. And that's been continuous for the last 4 years. And I've even said I'd actually like to become a student just to sit and listen because it fascinates me. You guys get that opportunity to do that, and you've done that. And you're going to continue to do that as you go into industry and you bring your knowledge and your own innovations like the professor did here. You know, he was a student. He's gone off. He's worked with NASA. He's built rockets. You guys are building rockets. You know, the future starts here in this university with you guys. But let's remember that who's giving to us today, these industry leaders, these professors, is what you're going to be doing tomorrow to the next generation that comes through. So remember where it came from. Always be thankful, always be grateful, but always share. Always share. Now then, I want to introduce one of my friends up onto the stage. I've not finished with you all yet, but I'd actually like to ask Tyler. Tyler Moses, can you come up for me? Say hello to Tyler. So Tyler, I believe you've got something particular to say.
I do, yeah. So, hi, I'm Tyler. I am this year's project manager for the MAC team, and I get the privilege of announcing the overall Society Award. So they're going to hate me for this, but I feel like this person needs the recognition that they more than deserve. This final award goes to an individual who's really stepped up this year, put in 110% into the society, and balancing it with a million other different things, but still showing up and being there for the team. Our society project is practically a full-time job with the amount that goes on behind the scenes, but except we get no salary or annual leave. But they've dedicated the hours outside the society time to make sure that everything's in place for this project to run. Even when things haven't been smooth, it's been dealt with quickly and professionally, and working alongside this individual this year has been an absolute privilege, and to watch them grow, both as a person and a leader, has been truly inspiring. From the get-go, they've been present week in, week out, developing like-minded individuals and giving their time of day, clarifying anything and answering any questions no matter what time it is. We've had many a technical talk between the hours of 12 and 2 a.m. Without their patience, humour and dedication, this project would not be where it is now, and we owe it all to you. I can't wait to see this year out with you. On behalf of the team, we're incredibly proud, and thank you for your commitment this year. I know it's been tough. I'm thrilled to announce that this award goes to Eleanor Foley.
Certificate or award, but we will definitely get something to you. But let's hear it. This is absolutely wonderful. Well done. Congratulations. Serious congratulations. So whilst we're on this vein, I just want to say that there's been a huge shift in what's been happening in our industry, and the Dean pointed out at the beginning, in the very first speech today, and she said, you know, women in engineering is important. Women are engineers. What's happening here today is I am seeing more women in here, more women on this stage contributing, and that's fantastic. Doesn't mean we need less men. It just means that we are encouraging each other, everybody equal, to say, actually, engineering's for everybody. Engineering is an opportunity for you to shine, for you to take your ideas and create something that's going to improve the way we live, or the way we drive, or in our case, the way we fly. And that's important. It's important that we have equal numbers of everybody. So I just want to say, continue encouraging those people around you that might not even think of engineering as a profession for them. Let's remember that word, profession. We are professionals. And we want as many people to engage in our engineering communities, because actually that's the bit that's probably growing the fastest. With the new technologies, we talked about AI earlier and how that's developing the way engineering looks, feels, works and operates. It's true, it is. And we're learning as a result of that. So make sure that you continue to encourage whilst you go off on your journeys and you explore the world, and engineering can take you anywhere doing anything, but encourage others to come with you. I've made a few notes so that I didn't forget. Ian earlier was talking about job opportunities when the panel were up here, which was a great panel session, by the way. And Ian said, you know, not everything centres around BAE. I'm going to agree with that. BAE is one very, very big noise in this area, it really is. And we love BAE. BAE is at the forefront of engineering technology development. You know, we look at what's going on there at the moment. And what's really important to remember is the businesses that surround BAE and companies like BAE, like Airbus and Rolls-Royce and Boeing, etc., those smaller businesses get the opportunity to innovate and innovate faster. And one of the panelists said, actually, if I'd have gone straight to BAE, I wouldn't have been able to shine in another company. Don't think that you have to wear the biggest badge on the market, because the biggest opportunity for you guys, and you guys are brilliant, are sometimes in the smaller businesses that actually allow you to innovate, allow you to bring your ideas, do something different and shine, because you make them shine at the same time. So don't always go for the big badge. Go for the career, go for the opportunity, go for what makes your heart sing and makes you stand out from the crowd, because you guys here have got the ability to do it. The job opportunities and the job market is a difficult place right now. I know that. We're trying to help students and we're trying to help businesses find people to fill those jobs. And it's quite difficult because the industry out there that, you know, they come and they will knock on my door every 5 minutes and say, we haven't got enough people. The big companies are stealing our staff and our skilled workforce and we can't find anybody. Then I come to the university and the professors and the mentors will say, we've got students looking for jobs and we can't find jobs. The companies aren't recruiting them, or they're not taking them on, or they're not interviewing them. Why? And I stand kind of in the middle on this bridge with my team saying, how do we close this gap? It's important that we close this gap. So we are working really, really hard at the moment to create something that is for you guys. I've mentioned it before, and quite a number of the professors and industry leaders are aware of it. We're creating and developing a website. Sounds rubbish, right? A website. Everybody's got a recruitment website. This is not a recruitment website. This is a student showcasing website. Every training organisation or academic facility that develops engineers or grows engineers, creates and helps our engineers, gets the opportunity to allow their students to post themselves on that website. This is not a CV site. I don't want to see CVs on that site. What I want to see is you. I want to see your personalities. What do you want? Who are you? Again, the panel, when they talked about it, they said, in fact, I think it was Ian, he said, we don't need to see the same words that we see on LinkedIn. The companies that are out there are looking for the person that's behind the face, the person that says, you know, I was part of the IMAC challenge, I was part of the teams within the university that have developed and competed in these competitions, and we've developed and innovated our own products and projects. That's what these guys are looking for. So we will make sure even the leavers of this year will still be allowed through the university to be able to put themselves on that website. And you won't have to pay for it, but you will have to manage it. That way we know that companies are looking at you. And we'll give you more information about that. But that's just one of the things we're trying to do to help ease the transition or bridge the gap between education and industry. And so I really hope, because I'm not going to witter on, because I think I've done enough of that, but I really, really hope that every single one of you actually succeed in everything and anything that you do, and anything that we can do, all of these people down here at the front, all of us, anything that we can do to help you, we are there to help you. Ask. If you don't ask, you don't get. You continue asking, continue knocking on doors. And actually, if you've got ideas on how we can do something to help you guys transition into the workplace, come and tell us. Give us your ideas. We'll work with you. We'll make it happen. So without further ado, I'm going to pass off to you now at the end of this really fabulous evening and say congratulations again to all of our winners. You are amazing. But actually, you're all amazing, all of you. The team that have helped put this together tonight, let's hear it for them. Let's say thank you, guys. Well done. But as Professor Robert Walsh will say, or probably not say, he'll tell me off afterwards, but you are the brightest stars in our galaxy, and we want you to shine. Shine, 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 and actually win big. Congratulations, guys, and thank you.
Thank you to Paula Gill for that presentation, and that unfortunately marks the end of the presentations for this evening. Thank you again to all of our special guests and our presenters from the NRC, from UAS and MAC. We sincerely hope that you've enjoyed this glimpse into the achievements of the Aerospace Society this year. Please stay for our expo section at the back. Refreshments, of course, will be provided. Thank you, good night, and get home safe.
Blue bubble gum twist around your tongue. I don't want you to get lost. suits your restaurant. Music for whatever you want. I'm not going to get lost. I'm not going to go wrong. Staying cool. If the stars were edible and our hearts will never fall, could we live with just a taste, just a taste? 'Cause I love you, babe, in every kind of way, just a little taste. You know I love you, babe.
Well, you can tell by the way I use my walk. I'm a woman's man, no time to talk. Music loud and women walk. I've been kicked around since I was born. You know it's alright, it's okay. If you can't look the other way, we can try to understand the New York Times effect on men. Whether you're a brother or whether you're a mother, you staying alive, staying alive. Feel the city breaking and everybody shaking, and we're staying alive, staying alive. Ah, 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 staying alive, staying alive. Ah, 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 staying Well, I get low and I get high, and if I can't get either, I really try. Got the wings of heaven on my shoes. I'm a dancing man and I just can't lose. You know it's alright, it's okay. You can look the other way. We can try to understand the New York Times effect on men. Whether you're a brother or whether you're a mother, you're staying alive, staying alive. Feel the city breaking and everybody shaking, and we're staying alive, staying alive. Ah, 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 staying alive, staying alive. Ah, 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 staying alive. Life's going nowhere. Somebody help me. Somebody help me. Life's going nowhere. Somebody help me. By the way I use my walk, I'm a woman's man, no time to talk. Music loud and women walk. I've been kicked around since I was born. You know it's alright, it's okay. You can't look the other way. We can try to understand the New York Times effect on